Want to help you all with some labs this week. I'm not there to show you what to do. The book is very detailed and it'll give you a lot of good information, but I thought I would give you some real life information in real time here. I'm looking right now at the surface weather map. This is Saturday morning. You're going to see a bunch of different weather maps throughout the course. Surface will be the beginning. Right here where we are. Surface is just right on, literally right on the surface of the Earth. So we have low pressure here at 1016 millibars. 1017 millibars could be higher, low. It's not much change, obviously. We have a front, kind of like a stationary front right here, where you have the semicircle warm front, triangle cold front, and they're just alternating. So that is a stationary front. That front's not moving. Down below that low, you can see a cold front sweeping through the Gulf of Mexico. Have another one coming down out of Canada up here, and a little bit of a warm front, and then back to a cold front here. A couple of things I want you to know. You're going to be looking to see on which side of a front you're on. Well, a front is always going to move the direction either this triangle is pointing or the semicircle is pointing. So, like for example, up here, this warm front is heading back towards Canada. Here, the cold front's heading south into the United States. The other line drawn on here are isobars. They're lines of equal pressure. So, if I am moving from low pressure here towards high pressure over here, pressure is rising along this line. And these isobars are showing that. They represent the different pressures, the 4 millibar differences from each one. So let's take a little more detailed look at a little corner of the world. So with that in mind, we're focusing right here on West Virginia, Ohio, Pennsylvania, Virginia, parts of Kentucky. You can see here isobars, and they're moving. They're directed all the same pressure. So if I assume pressure is higher up here, which it is, then if I go from here, where it's lower, across this way to where it's higher, the pressure is going to be going up. If I go the other direction, it's going down. And I want you to take a look then at the station symbols. There are a lot of observations around the United States, around the world. We're trying to get a map of what's going on. So I want you to, let's look here at Richmond, Virginia. Upper left on a station symbol is the current temperature in Fahrenheit. So our current temperature there at Richmond is 60 degrees. Underneath that is the dew point. So if I were to cool the temperature to where dew formed, that would be the dew point. That's how much moisture is in the air. In this case, it's 60. So there is a lot of moisture there in the air. I'm just looking on the left side of the symbol right now. So if I went out further north into Ohio, for example, here, we'll say Canton, which is probably this one, we'd have a temperature of 39, a dew point of 34. So you can see how there's 5 degrees spread there, but none here. So it's really quite moist here. I want you to also notice to the left of the symbol is 3 dots. Dots represent rain. So 3 dots means we have moderate rain. 2 dots is light rain. 1 dot would be like very, very light rain. 4 dots, making a diamond shape, would be very heavy rain. So when you think about the kind of precipitation you have at your house, most days it's probably rain if you have it. Other days it might be snow. Snow is literally a star. So you would have snow as a star in this thing. Other things might be drizzle, which are kind of commas, like looking like. So there is a whole list of these in your book of what they are. For example, here, the straight lines are fog or mist. Here's some snow. Actually, you can see it right here. 2 stars. So that is how you look at the left side of a station symbol. Now, on the right side of the station symbol is pressure. 196 here, 227 there. Well, we take pressures into 1/10 of a millibar. So if that's 1/10 of a millibar, 19.6 millibars is not a true pressure. The average atmospheric pressure is about 1,000 millibars. So with that in mind, then, something must go in front of this. What goes in front of this is a 10. So it's 1019.6, like 1017 here millibars, 1018, 1016 here. If we go up further, it would be higher pressures up that way. But this is 1019.6. Now, every once in a while, we get a pretty strong low pressure systems. And they tend to have, like, you would have a number probably here of 855, we'll say. Well, with that, you would put a 9 in front of it. So it would be 985.5 per millibars. That would be a fairly intense low pressure system. So all you need to do really for this course pretty much is if this says 0 to 500, it's probably going to have a 10 in front of it. If it's above 500, it's probably going to have a 9 in front of it. There are exceptions. You can get a very strong high pressure or you can get a very strong low pressure. But you'll notice it by the pressures around it. So now that we've covered pressure, precipitation, let's look at the middle, the circle. The circle indicates cloud cover. In other words, it's like your sky. If you're looking straight up into the atmosphere, in your sky, and it's completely covered with clouds, that's that symbol. Now, take a look up here in Pennsylvania. We have just a little bit of the sky covered. So maybe partly cloudy or scattered clouds. Out over the water, you'll see an X here. That's fog. It's an indefinite ceiling. In other words, I can't determine. I know the sky is covered with something, but when you look into a fog, it may be very low and it's very difficult to see whether there's really clouds or just a big patch of fog over top of you. So that is what you're seeing here. All you've got to look in this symbol is just at those things. Here, there's a little bit of fog, but not the whole sky is covered. Finally, the hardest one is wind. You'll notice, think about this as degrees. In other words, you started here at 0 degrees or 360. If you went over to the right, this would be about 90 degrees. 90 degrees is an east wind. 180 is a southerly wind. 270 is a west wind. This wind is coming out of the east. So we would say we have an easterly wind. So in other words, the air that's coming into Richmond originated somewhere over this way and has moved in. Now, if I went back to some of these other areas, like out here in Indiana or Illinois, notice the wind's out of the northwest. So it originated to the north and west. Think about it. If you live in your area and you have a wind coming at you from the north, to the north of you is probably going to be Canada. Well, it's probably going to be colder air. If it's coming out of the south, it's probably going to be warmer air. It's a general rule of thumb you can use for the wind. So this is the wind direction. Speed. Notice this little barb right here on the end of this wind. It's a little tiny barb. It represents 5 knots. Notice we have a bigger barb here. That represents 10 knots. So you just add those up. So if I had another little barb here, it would be 15 knots. If I had a couple of the big barbs, it would be 20 knots. That's how you determine the wind. The more barbs, the stronger the wind. And finally, if there's no wind, it's just another big circle around the station symbol. There. Any one of these observations now is that way. So whenever you're looking at a surface weather map, you've just looked at them. Finally, let's move on a little bit here. All right, now I just pulled up a map of the different areas here, and I want to look at what has changed. It's called a meteogram. You're not going to see this for a few weeks, but you will see some of these. And on it, literally every hour, we have taken the relative humidity, the temperature, and the dew point. You're never going to see the dew point above the temperature. It just can't happen in real life. But you'll see that where they're close together, the relative humidity is very high. Where they go apart, notice the relative humidity comes down. The temperature goes up. These are taken literally every hour. So in other words, if I go along here and read them out, I can go right down here and find the hour that they occurred. This is a 72-hour map. And if I wanted to look at something besides these, say I wanted to look at pressure, for example, I can go in here, find air pressure, sea level pressure, and notice that the air pressure was rising, and it started to fall, rise again. Now it's back down again, coming down. So you can see at this location at Parkersburg, we had a rising pressure, lower pressure arrived, rising pressure again, then lower pressure now. This is how you read a meteogram. If you have questions, please ask, but this is just an X scale here with the time, and a Y scale with some other variable or variables. All right. We're going to look a little bit now at the upper air. This is a Stuvie diagram. All a Stuvie diagram is plotting a temperature, which is always going to be on the right, a dew point, which will be on the left. You'll notice down below are temperatures. Since both dew point and actual temperatures are degrees Fahrenheit, in this case they're degrees Celsius, so 0 degree would be freezing. So we go below freezing right here. Off to the left are pressures. When you go up in the atmosphere, the pressure gets less. So at this location, we go below freezing, roughly about 680 millibars. And you see it keeps getting colder. Right here is literally where the tropopause is, the top of the troposphere. You can see temperatures begin to warm at that point. That is where the stratosphere comes in. So when you're looking for how moist a sounding is, like this is called a sounding, an upper air sounding, the closer they are together, the moister it is. You can see there's a little bit of a break here. Little distance. It may not be too much in the way of clouds in this area. If you were a pilot, that might be a place to fly through. You'll notice up here, once you get to the stratosphere, it gets very dry very quickly. So now you should be able to, if I told you I want to know the temperature at 500 millibars and I gave you a sounding, you go up here to 500 millibars, go across. Right there is your temperature. Look down, approximately about minus 13. Finally, on the right are the winds. We've been talking about them as being barbs. Just think about a circle in here. These are all southwest winds here, southerly here. Here's an easterly wind, a northerly wind at the low levels, very light. But then it becomes southwest, southerly here. And notice the barbs picking up. There we have 35 knots. Here we have 45 knots. And here, a pennant and 2 barbs. A pennant is 50 knots. So here would, for example, would be 70 knots of wind. Up here, getting near these are in the jet stream, that's 130 knots of wind. So we've now started at the surface. We've looked at how you read a surface map. We've looked at how you read the SKU-T or STUV diagram to know the temperatures and how things change as you go up. Let's take one last peek at an upper air diagram. This is 500 millibars, halfway up the atmosphere. Notice these are contours now. Contours, height lower. So in other words, if I had a perfectly horizontal surface, the pressure would not stay the same along that line. It would be one thing over here and another over here. This is lower in the atmosphere. This is low pressure aloft because it's been compressed down. This is high pressure aloft. And you can see winds are blowing out of the southwest here, out of the northwest here. So you're going to be seeing these more and more. I just wanted to give you an overview on them. Hope you got a little bit out of this. Please don't hesitate to ask because I know the labs are hard, but I want you to do well in them.